take it away.
Yeah, thank you so much for the invitation. I wasn't expecting that many people, so it's very exciting to be here. So I'll be talking about the project in economics. So just for background, I'm an economist. I work mostly in electricity markets. This project is actually looking at the demand side of electricity. We'll be trying to measure what are the gains from doing energy efficiency projects in schools. In particular, I will be looking at public schools in California, and the project indeed has a bunch of people from the University of California system, and also with Chris Needle at MIT. So you can see the title, it says machine learning from schools about energy efficiency. So the idea of the project is to see to which extent the tools that many of you are probably way more familiar with than myself are already using in your fields. So we want to see how these tools, machine learning tools, can be useful in the context of economics, and in particular in the context of estimating energy efficiency effects from policies. So for those of you who are not familiar with what energy efficiency is, it's basically a set of measures that we hope we can undertake to get the same kind of service from energy, but using less energy. Lighting is a good example. We get the same light, but all of a sudden we're cutting by a third or we're cutting by a quarter what the light bulb needs to produce the same energy. So this is energy efficiency, and it's believed to be a sort of untapped resource, and much of hopes have been deposited in energy efficiency going forward. So this is just to give you an example from a report from the EIA, and they were saying, okay, going forward, end-use energy efficiency will be about 42% of the reductions that we hope to achieve in the future. Now, when it comes to practice, measuring energy efficiency, it's a bit tricky than what it seems. And both engineers and economists have spent a long time trying to think, okay, if we undertake some energy efficiency measures, how can we quantify what we're getting out of that back? So what's the return on those energy efficiency investments? What makes it hard is that when we think about energy efficiency, to see what the benefit from energy efficiency is, we would like to see the same unit, let's say a house or let's say a school. We would like to see them exactly with the energy efficiency and without it. This is what in economics we call the counterfactual energy consumption, what they would have done if you would not have done such a project. But by construction, that thing is never observed, right? If we do the energy efficiency project, they already did it. And if we don't do it, they haven't done it. But we cannot quite compare them both at the same time. So there are several approaches. So many of the approaches to energy efficiency when it comes to policy are based on ex-ante simulations. These will be often very detailed engineering models that try to predict what are the benefits from doing some energy intervention. These are often also used to compensate these energy efficiency measures. So a big part of the policies surrounding energy efficiency, they give incentives for firms or they give incentives for households to undertake these different measures. The way they compensate them, it's often with ex-ante simulations. What are some of the benefits? Well, some of the benefits of ex-ante simulations is that it's very transparent in the terms of what the assumptions are that gave you the number about how much energy you will be saving. So those are some of the advantages. The disadvantages is that they do not take into account things that might be outside of the model. In economics, for example, we worry quite a bit about households or firms or individuals changing their behavior after they have their new energy efficiency measure. So imagine I got a new light that's much better than before. Maybe I will use it more often, and that will usually not be part of an ex-ante model. An ex-ante model is usually more of a physical model, but it's harder to take into account how people behave. Other approaches to measurement are just doing an ex post before and after comparison. This would be narrowing down into just a single unit, let's say a house, or narrow down into a school, and try to see before and after how the school is doing. The advantage is that we can really narrow it down to that particular school. We probably know a lot about the school, but there are, of course, clear disadvantages. Typically, when we do a before and after comparison, also known as an event study, we worry that other things are changing at the same time. So imagine there's a before, the school doesn't have an energy efficiency project, then we do the project. It might well be that after that, there are some trends in energy consumption that are making consumption drop or consumption increase, but that would be true even if they had not done the energy efficiency intervention. So with a before and after comparison, those things are hard to control for. So in economics, there's a big push for randomized control trials, and also in the context of energy. And basically the idea there is that we will have some agents, let's say households or maybe schools, and we encourage them randomly to incorporate some of those energy efficiency measures. And then we base the comparison between the schools that did it, the schools that didn't, and before and after. So this is sort of an ideal setting, although it also comes with some drawbacks. The first drawback is that it tends to be expensive to do this kind of randomized control trials. And because they are expensive, it will tend to be very narrow. So we will be looking at a few schools that we managed to incorporate into that project, or we will be looking at a few households that we managed to incorporate into the project, but we might not be able to look at everyone. So what I will be talking today mostly is the last one, which is a difference in difference approach. I don't know if you are familiar with this expression. It's quite simple. It's comparing units that actually did a project and units that didn't before and after. And this is why the difference in difference comes from, because it's before and after, but also units that did and units that didn't. So it's the same as the randomized control trial with a very important difference, which is that the schools that did do these energy efficiency interventions are not necessarily the same as the ones that did not. So that comparison becomes a little bit less clean, but at least hopefully empirically relevant. So the scope of the project is to measure this before and after. Again, it's not a very complicated paper. Our main focus, though, is to try to see how machine learning can help us make that comparison cleaner. And I will be more clear about it as we go forward. When it comes to policy, the big question will be how do these exposed savings that we can quantify in the data compare to the ex-ante savings that came from the engineering model? And again, this is very important for two reasons. One, I guess it's good to validate how our ex-ante engineering models are doing. But second, because incentives, as I said, for these policies are based on these ex-ante engineering models. So it's sort of important to see how well those ex-ante predictions match what we can measure in the data exposed. So in terms of contributions, what we hope is to bring in this machine learning methodology to the basically econ turf. Many of you will be familiar with things I will be mentioning. I will be talking about lasso and things like that. There are many other machine learning tools that we can use. We are not very married to a particular machine learning technique, but rather we want to understand how machine learning can help in this setting. And we find that machine learning helps us in two main ways. One, it allows us to choose from a wide set of covariates, as you might be familiar with. But another one is that we feel in the context of energy efficiency, it can help us quite a bit with the variance bias trade-off. And in particular, when we have measurement error, it will help us get estimates that are more stable. Yeah, let me just mention this. The bottom line will be that when we use machine learning, our estimates will tend to be larger and more precise. And I'll be more clear about why we think that's the case. In terms of policy, these are important policies. So the nice thing about the project is that we could get the Public Utility Commission to share with us the smart meter data for all the schools in Northern California. And with that, we will be able to measure the efficiency from these projects. These are relatively modest projects, so we will find that they save about 1 to 3% energy when we use the Diff-in-Diff approach, and 2 to 5% when we use the machine learning approach. Importantly, for the bottom line I was mentioning, we will find that the exposed estimates of energy savings are not too far from the ex-ante expected engineering savings, we find that 70 to 90% of the ex-ante savings seem to be at least happening in the data on average. This might look not the best, it's not 100%. For the scientists in the room, you want it to be, perfect. But for the economists in the room, actually most of the literature had been finding that the expected savings were massively overstated. They were much larger than what we actually could measure. And in this project, I would say we have a bit of a half-full story because we find that most of the savings were realized. Again, in contrast with some of the other literature that finds that basically the policies were not worth 10% of what people expected or something like that. So it will be on the relatively positive side of the economics literature, but still on the relatively negative side of the engineering literature. That's how I would put it. I don't know if there are any questions, but this was sort of my introduction to motivate the project. Gonna jump in and talk about the context and the data. I will be a bit fast so that we have time to talk about everything. So the motivation for the project came in 2012. So in 2012, California passed a law to close a loophole that generated some revenue to the state. And basically the state decided to spend it on energy efficiency at public schools. So the tax loophole had nothing to do with public schools, but you can see how politically, and especially in California, it was seen like a good thing to spend money in energy efficiency and also in public schools. So this is how the thing got approved. They decided to spend $500 million for 5 years on energy efficiency measures at these schools. Initially, Catherine Wolfram, one of my co-authors, she was trying to encourage the states to randomize these $500 million per year. That didn't work too well. So these $500 million are being spent, but they are not being spent randomly. Instead, what we sort of have to do is look at the measures that are happening over time and just try to see how well they did, but understanding that it's not an experimental setting. Okay. Actually, our data will go back to 2008. So we will have many, many measures that come before this $500 million. It's not that the schools were not spending money on energy efficiency. It's just they were not spending nearly as much money. Our data is until 2014. So again, for the most part, it will be before this Prop 39, but we hope that at least this could be useful going forward. We have about 2,000 schools in our sample. Potentially, there are many more. In California, the population sample is about 10,000. The reason we have 2,000 is because we focused on a particular utility that's working in the north of California. So out of those 2,000 schools, even before Prop 39, many of them were already engaging in these energy efficiency projects. It would be some sort of rebating for new lighting or rebating for having a better HVAC system, air conditioning mostly. It would be some incentives for replacing the fridges at the school or other cooking appliances at the school. So it's basically a battery of incentives to make the schools more energy efficient. For each of the schools, we observed when they took the measures, what the measure was, what the expected savings from the measure were, how much it cost them, and a bunch of other characteristics. On the day-to-day basis, what we do have is 15-minute data of their electricity consumption. So for every public school, we will see every single day what they are doing with their electricity. And then basically for the purposes of statistical power, we'll focus on 2 interventions that are most common, which is the HVAC, heating and air conditioning, and then lighting. So let me show you what data looks like for a given for a given school. So this is an example of one school who had an HVAC intervention. We know the date of the intervention, so we centered the data around that date. And for every day, again, we have a bunch of dots with their electricity consumption. Thinking about yourself, electricity consumption is very volatile during the day. This is aggregated at the hourly level, but you can still see that some hours we consume a lot, some hours we don't consume much. This is sort of deemed to be centered around 0, but what you can see is that we have the before and after comparison. So again, some approaches to measuring this would be just to take this data from this single school and call the effect of the intervention the average of the black line minus the average of the blue line, or some version of that comparison. In this particular case, it does look like they did save some energy. What happens though is that other things might be changing over time. So usually what we do is we rely in much more many schools. In our data, we have plenty of schools. For example, we have this school who did a lightning project. And for this school, actually, the average doesn't look like it changed much. Although if you look at the distribution, you could say that maybe they cut consumption and maybe quite a bit, depending on how you look at it, in the very peak hours, the hours in which they were consuming the most. Again, what we will be doing is taking this data for many schools, 2,000 schools, and then we will be sort of averaging out these different comparisons so that we can know what was the average effect of these policies. The first part of the analysis is very standard, at least in economics. Yes.
Question. So you marked their day of upgrade, and I can imagine if you are switching a air conditioning system, maybe there will be a couple of days in which you can't replace that. But if you are replacing the lighting, will it be like that, or it's kind of done over a longer period of time in which the janitor or something can't change this today, changes in this room, and then tomorrow it's going to change in another room, and so the transition is not as sharp or as on day 0, but it's extending over a period of time.
Yes, this is a very good question, and it was one of our concerns. Actually, a first order concern is also how is that date recorded? Because even if you thought they do it in one day, I would be very skeptical to think that they actually recorded it in that.
The schedule versus the actual.
Exactly. So there are many reasons to think that that date is sort of a moving target. So we think of our approach to machine learning as dealing a little bit with that concern. I will explain more clearly why as I get there. But our sense is that indeed putting too much faith on this exact date is very tricky. The other reason is tricky, hold on a second, is that many of them do it either in the winter break or the summer break. So you might be tempted to be like, okay, I will compare the day before versus the day after, but or the week before versus the week after. But it might well be that there are no kids at the school, or that there are no kids, and then all of a sudden, like 500 kids show up. So the comparison as we get closer becomes very, very fuzzy. Yes. So for now, I will be showing the average intervention, what the percent reduction was from the average intervention, but of course that can be quite misleading because there's huge heterogeneity. At the end of the talk, I'll talk about the intervention per kilowatt hour expected savings. So it's a way to scale up and down the size of the interventions. Now, it's not the main focus as of now because we had huge errors in the database for that measure, as well as the costs from the interventions. We just got the data like yesterday, so I couldn't possibly run the whole thing before today, but now we have better data and we will make that more of the main estimate. For now, I'll show just the percents because they are less confounded by this kind of huge measurement error. Yeah.
Can you comment on the power sources? How much gas were there transitions where they switched from electricity to gas?
So we have the gas data. We haven't incorporated it yet, but we know whether a school is heating with gas or with electricity. Our expected savings, for example, the measures constructed, they do take into account the spillovers between gas and electricity. But for now, the analysis is still work in progress and it's only electricity for now. But potentially we can do it. For gas, we wouldn't have the day-to-day, but we would have the monthly gas bills.
You might be able to see if someone switched from electricity to gas, how much the electricity drops. So right now, you don't know that total bill, how much is lights and how much is so on, right?
Yes. So we do not know. We do know, however, if they replace the HVAC system, we know whether they are replacing it for something that's not electricity. That we know. And my recollection is that there's not much switching, but we should have a more careful look. But we have that information in the data. Actually, we know exactly what they are putting in place and what they are replacing. So in principle, we can do much more. Yes. So the regression analysis, again, very standard in economics. It's what we call a diff-in-diff. And as I mentioned, it's basically a comparison before and after between schools that did projects and schools that didn't. So if you think about the, yes, question? Okay. So if you think about the regression, what we will be doing is having the consumption of the schools, and then we will be including a bunch of things to control for heterogeneity among the schools. But then the main variable of interest is this dummy variable, an indicator variable of whether a school did a project or not. On the before period, it will be 0 for everyone, and in the after period, it will be 1 for some schools. So the comparison is this before and after between the schools that did it and didn't do it. The interpretation, again, it's sort of tricky when measures are so heterogeneous, but it will be the average savings from an energy efficiency intervention at these schools. Now, the concern from the Diff-in-Diff approach is that the schools are very different, the ones that are treated versus the ones that are not. In our data, for example, larger schools, typically high schools, are much more likely to engage in these policies than, for example, an elementary school or a middle school. So doing that comparison is a bit tricky because, again, we want to make sure we do some apples to apples. So in our approach, definitely, we will include a fixed effect, a dummy variable, an indicator variable for every school so that we at least the consumption at the school level. And I will show you that we can control for other things parsimoniously. So the average savings that we find are about 4%. This is when we include a school fixed effect, so we control for relatively little. As we control for more stuff, we find a smaller effect, and basically in one of the specifications, we find a 1%. Now, this is a typical challenge in economics and in many other disciplines. Depending on what we include, we'll get a different number. And for policymakers, of course, they would like to say it's 4%. If you are a researcher, you might be more comfortable with the 1%, and probably you still want to do some more. I'm just showing you here a sample of specifications. And again, the savings appear to be between 1 to 4%. There are many, many observations, as you can see. So here what we did is work with data for every 3 hours instead of every 15 minutes, so that we would have a little bit fewer observations, but still a very large sample. All the standard errors, for people who care about the standard errors, are clustered at the school level. So even though we have 20 million observations, in reality, we have 2,000 observations because we have 2,000 schools where things happen, okay? Now, we are, I guess, looking at the average savings is a bit misleading because these interventions are not supposed to work all day long. For example, if you think about HVAC, it's supposed to work when you have your AC functioning, or lighting, it's supposed to work when you have your lights on. So what we wanted to do is check the profile of these savings across different hours. So here what I show you is the savings from HVAC across different hours. And to our surprise, these estimates were sort of all over the place and definitely not in line with what you would expect from an HVAC system. So this is telling you that the HVAC system saved at night and didn't do much during the day, which again, it's not the most intuitive. We also found that it was quite sensitive to the specification. Going back to the challenges of running the regressions. As we control for more things, we can see that these effects are really very, very noisy. So the bottom line is that we cannot say much for the HVAC systems, and the profiles seem to be somewhat funny. Now, when we look at lighting without many controls, so when we control for very little, we do find very weird patterns too. We find large savings at night and not many savings during the day. Maybe schools are really leaving the lights on all the night, but it's really not the most intuitive pattern. We see that as we control for things, we find more intuitive patterns, and actually for light, they are very stable, and they are about 5%, although again, depending on the specification, they might become a bit smaller. Yes.
So with the cooling, one of the biggest issues is actually what the outside temperature is. Do you include in the analysis information about what the maximum temperature of the day was or something like that?
Yeah, so we have some regressions where we have that, and it's going to come now in the machine learning.
Oh, okay.
Yes, yeah, so we will have that in there. So this is just to give you a flavor of what the regressions give, but basically overall, they do show some savings, but they seem to be quite sensitive to the specification. And we still were concerned about whether we are missing something, whether we're comparing schools well enough. And again, part of our analysis in the regression suggested that it was very tricky to make these comparisons well. Part of the reason is that these things are very granular. Electricity consumption is very highly nonlinear. Sometimes you consume a lot, sometimes you consume little, and it might be very interdependent with weather. It might be very interdependent with the month of the year. So there are many potential interactions you should worry about so that you make that comparison as kosher as you can. One red flag that we found is a placebo test. So in the context of Diff-in-Diff, we often call a placebo test when we take the data only from before, we throw away all the treated data, and we basically make up a treatment. So we come up with a date and we make up that there was a treatment that date. And then we try to see, okay, if we run the same regression, would we estimate some treatment even though we know by construction that we just made up that treatment? So this is what we do when we do this placebo, and the idea is that it will be a red flag if we pick up something spurious. We found that on average, we were not picking up anything spurious. So our placebos were more or less zero on average. But what we found is that we were getting many confounding factors when we looked at the heterogeneity of these interventions across hours. So these are the lightning placebos, and as you can see, there are very systematic patterns that the placebos are picking up. In this regression, we actually included an indicator variable for every school, but also every school interacted with each hour. So there were like 2,000 times 24 kind of controls to saturate the model. What we thought was saturating the model quite a bit, but it really didn't saturate the model, and that came as a surprise. So this is when we started thinking that we needed a more systematic approach to control for the differences across the schools. Because the regression, as much as we thought we were saturating the model, it wasn't cutting it. So this is where we started to turn into machine learning. Again, the idea of the machine learning is that it will help us control for the right things and in a systematic fashion. So let me get into the machine learning. So here, as researchers, we were facing an important trade-off. So when you have a regression, at least in economics, we want to control for as many things as we can. But for all of the applied researchers in the room, we know that if we start throwing things into the regression, eventually we're left with garbage. And this is this variance bias trade-off that if I keep adding things into the regression, eventually I'm left with very little variation and not the variation that I thought I was going after. So in the case of schools, it's very easy to control for things. We have temperature, we have the day of the week, we have whether it's a holiday, we have all the hourly things. And on top of that, very importantly, you can interact all of those things. What's the effect of temperature on a Monday? What's the effect of temperature on a Monday at 3 a.m.? What's the effect of temperature when temperature is high on a Monday at 3 a.m.? Okay, so you can really go very creative very easily. So we easily came up with 6 million control variables. Now, I'm cheating a little bit here because what we came up with is about 3,500 variables per school. But then we wanted every variable to be school specific. Why? Because every school is a world on its own. So then you take 35,000 variables, you make them school specific, you come up with easily 6 million variables. That's clearly not efficient. We couldn't afford to run it that way anyway. But ex ante, it was sort of tricky to think, okay, how do we pick among those so that we make sure we do a good job? One thing that made it particularly challenging here is that for some schools, we had a lot of data, and for some schools, we had little data. The reason is that the schools don't necessarily have the smart meter at the same time. So for some, we had 5 years of data. We can put many, many variables if we have 5 years of data. But for some, we had a year and a half. Or for some, maybe we had like 3 months. So try to put like 3,500 variables if you just have a week. That's not going to work well. Again, ex ante, it would be very hard to make a choice on how many variables to include, but also how many variables to include for each school separately. So this is why we turned into the machine learning, and we thought machine learning actually here could do very well. Machine learning, I am using it very loosely, so sorry for the experts in the room, but basically we think of it as methods that help us in prediction, in making prediction more efficient. And we thought it would do very well in the case of schools because electricity is something that's actually quite easy to forecast. Every day, the electricity that we get, it works because we have good prediction models that tell us how much electricity we need, and we just manage to produce it. So it's sort of easy to predict aggregate electricity consumption. At the individual level, it's much harder than at the aggregate, but the schools, in a sense, are sort of an aggregate collection of little kids and teachers, so they will be much more stable than, let's say, a house. If you think about your electricity consumption, it will be very hard to predict. But if you think about the electricity consumption of 100 people, that will be much easier. Another good thing about the schools is that they are not very exposed to the business cycle. So if you think about the school and it's a recession, we do have data from 2008 in there. It would be very hard to think about manufacturing and their electricity consumption in 2008. But for schools, they kept opening the schools. They might have been slightly more budget constrained, but for the electricity usage, it's sort of less likely that there would be big confounding factors. So prediction can do well. So we will use prediction methods to try to better control for these differences across the schools. So what's the approach that we propose? So in our first step, we will use only pre-treatment data. So we will throw away all the treated data, and we will use pre-treatment data to predict what the schools will do after. So this is sort of the the before and after approach. Think of taking one school at a time, and for every school coming up with a model that tells you what she will do after, and then just comparing what it really did to what we see in the model. The nice thing is that by doing it for every school separately, computationally, it's much faster, but also it's very flexible. We can be very flexible for every school. The particulars of it, we use the lasso method, but as I said, it's not that we are too married to the lasso method. Any usual suspect in the literature, I think, would do for our purposes, although they clearly have differences in the details. What this model basically gives us is the set of variables that we want to include for every school. Now, control schools, we don't have a treatment date. They didn't ever do an intervention. But basically, we randomly set a pre-period. And you can think of the control schools as being a good test of how well the model is doing. So if you manage to do a good prediction for the control schools, nothing happened there. So it's sort of telling you that the model is doing at least good on average. Once we have this prediction for every school, what we can do is look at the differences between their actual consumption and our prediction and focus on that in our second step. So the second step is the same as the Diff-in-Diff, but the only difference is that we are changing our Y variable, our dependent variable. Instead of looking at electricity consumption, now we look at differences in electricity consumption between what the school did and what we managed to predict. And in that regression, we'll still have the prediction before and after for treated schools and non-treated schools. So during the before period, by construction, the variable will be on average 0 at every school because the prediction is precisely trying to get the 0 in that range. For the exposed, ideally, or the after, ideally, it will be 0 for the control schools and not 0 for the treated schools. And this is the kind of difference that we will be doing. So in graphs, and this is a very self-serving simulated graph, we have data, we come up with a model that fits the data very well. Then we predict going forward what the school should be doing. This is a treat at the school. The school did that. So we compare that and we say, okay, this is the effect of the intervention. Now this is very beautiful looking. It's fake. In practice, these things are way more noisy. So instead of just looking at one school, we will look at how these differences compare and we look at schools on average. Okay, again, this idea of the diff-in-diff, that we just don't want to look at one school at a time. We want to compare them. We want to compare them on average. So some of the advantages, and I will go a bit fast on this, but basically the advantages, I already mentioned them as I was explaining it. It helps us parsimoniously select the variables. The prediction error will be much more homogeneous than the consumption at the school. So the consumption at the school can be very different. Some schools are large, some schools are small. Even if you take the log of that consumption, you can think it will be quite different. But if we think about the prediction error, it will be much more stable. Now, the third advantage is that, as I said, we do it school by school, so we can be very rich without the computational burden. We can run these things relatively fast for all the schools. And then finally, and this is something related to the using only pretreatment data, because we only use pretreatment data, we can play with the cutoff of what pretreatment data are, so that we don't worry about the treatment effect being contaminated in the selection process. So one challenge when we have the treatment effect that's very poorly measured is that as we try to pick covariates, it might be that that treatment variable ends up picking covariates that are sort of contaminating the effect. When we do the selection variable process, we don't have the treatment variable at all. So it's not even part of our first step. So there's no way that that can contaminate the process. And we find in Monte Carlos that actually this can be helpful from the method. Now going back to the application, recall that we had two main steps. I will show you a little bit what we get from each of these two steps. So the first step is predicting for every school what will happen. And the second is running the diff-in-diff, the same as before, but now using prediction errors as our main variable. So this is showing you what the model picks up. Every dot in this graph is a school. Here I put how many observations we had in the pre-treatment, so how much data we had to inform the model. And here I put how many coefficients we got in the Lasso model. So the Lasso model, for those of you who are not familiar with it, it picks the relevant coefficients and it sets to 0 all the rest. As I told you, for every school we have about 3,500 candidate variables. And as you can see is that the Lasso model is being quite parsimonious. By the way, on those variables, I didn't explain it very well, but we basically have a splines for temperature, a splines for seasons, the hour of the day, the holiday or not, the day of the week, and then many, many interactions between these things. Okay, so what you can see is that on average we only pick 100 or maybe 50 of those variables, but you can see that as we put more data, we can afford to have more variables. This is again one of the advantages of using this method school by school. For some schools we can afford to be flexible, for some schools we might not. Another thing that I want to emphasize is that even though on average we get 50 variables or maybe 100 for some, if you take the set of the variables that they pick across all the schools, they do pick the 3,500 variables. So it's not that they come up with the same variables. It's just that for each of them, you only select 50 or 100. So this is another way to emphasize why this is useful, because if we were doing a regression, we would be probably putting the same variables for all the schools. And then we would have to come up with 50 or 100, which maybe it's not too hard, but they would have to be the same 50 or the same 100. And here we actually cover 3,500 different definitions, but we allow them to be different school by school. One example for that is the holiday variable. So we have an indicator variable that tells us whether it's a holiday or not. And as you can infer or guess, being on a holiday reduces electricity consumption. It seems relevant to the model. Now we could decide to include only the holiday dummy. We could decide to include the holiday, but also take into account which season of the year it is, or include the holiday dummy and take into account what's the weather like that day. So we could do all these different interactions. I think we included up to 50 different holiday variables. And for most schools, honestly, only 1 or 2 were enough. They were including the holiday dummy, and that's it. But for some, they included up to 50 holiday dummies. So again, that's something that it would be very hard to do in a regression. By doing it in this machine learning approach, what we make sure is that the coefficients on these variables are not too crazy. If we tried to force the 50 holiday variables for every single school, we would get very, very crazy numbers. But by restricting the number of variables, we find estimates that are not, we don't have massive outliers. And for the most part, they are all negative, which is intuitive. Holidays are reducing electricity at the school level. So when we look at the predictions and how well we do, this is the distribution of errors for the control schools. And it's nice to see that for the control schools, the prediction is actually centered around 0. This is only looking at the after data. So it's completely out of sample. And completely out of sample, on average, we get that the predictions actually don't have any error. It's definitely not true for a single hour. It's definitely not true for a single school. But at least on average, we are getting good predictions. Now I'm going to show you the distribution for the treated schools. And sure enough, they overlap quite a bit. But you can see it's clearly shifted to the negative end. Negative in this setting means that our predictions are too big. It means that the schools are actually saving electricity. So just looking at the raw predictions, we can already see that there seems to be a treatment effect. There seems to be a reduction in electricity consumption when compared to the control schools. Now what we will do is put this distribution of errors into a regression context. And what you can see that the estimates are now between 5 to 2%. Importantly though, you can see that it still matters whether we control for more staff or less. And this is not surprising because, as we mentioned, these are schools that are not selecting into these things randomly, and there might also be confounding trends. So it's still important to control for some common trends. And this is what the month of sample is doing, or the month of sample control is doing. This is a time trend. But overall, we find that the estimates are comparable to before, although slightly bigger. Some of them are more stable depending on the specification. Now, importantly, we find that the heterogeneity in the patterns is much more meaningful than before. So here you can see the HVAC savings. And what the HVAC savings are telling us is that most of the savings accrue during the day, which is, to us, more intuitive. We were a bit puzzled by this spike at 6 to 9 a.m. If we went narrower than this, we really find it really at 6 to 7 a.m., that positive spike. It means that we increase consumption. So we talked to some engineers, and they told us that indeed, many of these newer systems are meant to consume more at 6 a.m. because they actually are more efficient at shutting down and then doing pre-cooling and then getting ready for the kids to come to school. So it was much more reassuring that with the machine learning, we are finding patterns that are more stable. The estimates still change significantly if we control for some of the trends, but they are much more stable again in its shape and much more intuitive when we think about the implied or expected benefits of these policies. The lightning ones, we have an outlier there in our predictions. It was generating this, but as long as we control for enough for these outliers, then we find that they are very, very stable. And again, much more intuitive. Lightning appears to have the biggest effect during the day. It's when we are expecting to see higher reductions at these schools. So our final test is going back to our placebos. So how well did we control for these confounding factors? Here I'm showing you a very small snapshot of what we can do. But our paper, we can look at heterogeneity in temperature, we can look at heterogeneity across different schools. And basically, the approach is suggesting that the machine learning will be better at looking at those different heterogeneities as we chunk the data finer and finer. So the question is, how well did we do to control for these confounding trends? Are we really doing a better job at looking at this heterogeneity? And basically, this is from before, where we had these sort of massive trends in our placebos. The placebos are the gray line. You can see the massive trends in the placebo. All our placebos are below 0 in this range. As we move into the machine learning, we can see that our placebos now are centered around 0. And all of a sudden, in all of the hours of the day, we can see that we have both positive and negative placebos, suggesting that we are now doing a much better job at capturing this profile of energy savings. This is, as I said, an example where we look at the profile of energy savings across hours of the day. But this will also be important if we look at the percent savings as a function of temperature, or if we look at the percent savings as a function of a school size or other things. So we feel that this is really helping us control for heterogeneity across schools. Okay, so I promised you this was a half full kind of paper, half glass full. And this is where it comes in. It's about program evaluation. So our motivation for this project was to see how are these estimates comparing to the actual ex-ante estimates that were used to incentivize these policies. Again, incentives are usually based on ex-ante estimates. So to do that, what we will do is compare our estimates to these engineering savings by running a very similar regression, but now the y variable will be electricity consumption, and the x variable will be the expected savings. So if beta is equal to 1, it will mean that on average, we are getting the same savings as we expected ex ante. If it's below 1, it will mean that we are getting less than we thought. And if it's above 1, it means that we're getting more than we thought. Unfortunately, we cannot say what generates that number, but it's the first number to see how well we are doing. Now, when thinking about these regressions, it is important in economics, and I imagine in other fields too, measurement error can be a big challenge. I don't know if you're familiar with measurement error, but typically when you have something measured with a lot of error, you will tend to find a small coefficients. Now, why is this relevant here? Policymakers want a big coefficient. And if you have a lot of measurement error, it will be extremely hard to find that big coefficient that the policymaker wants. So we feel that in this context, this machine learning can also be useful. Because again, for a policymaker, the bigger the better. For a researcher, we just want the right number. We don't know what it is. So machine learning can at least provide a handcuffs or something that force you to look at it in a particular way. For our purposes, the variable in itself is measured with huge error. So if we look at all interventions of our sample, what we find in line with the economic literature is that these measures didn't deliver at all what was expected from them. Actually, this means they delivered 7% of what was expected, and this one 15% of what was expected. Now, for the Diff-in-Diff, as we control for staff, these numbers are changing wildly. And if I go to the policymaker, I could just pick column 4, and you would get a perfect 0. So this means that these interventions are not working. Now, you might be like, hold on a minute, Mar, you told us that they were saving 5% on average, so why did it go to 0? And this is in part driven by this measurement error. We are now using these expected savings, and we're getting this beautiful 0 in here. The machine learning, which is one of our goals, is much more robust to such measurement error, but still it's giving us this very, very small number. The measures are delivering 10% of what was expected. So looking at the data, there was some obvious measurement error. Some expected savings were 600% of the school's consumption. I would put that in the typo category because it's very hard to reduce your electricity consumption by 600%. Try at home, you'll have to go on your treadmill and become a net seller of electricity. I don't think that's what people do. So clearly there was a lot of measurement error. So to take a stab at this, we looked at 2 of our measures that are better measured in a sense, and that would be the HVAC interventions and the lighting interventions. These are much more standard measures, hopefully better quantified. And indeed, we see something extremely different. By the way, these interventions are the bulk of what we have. I think it's about 3/4 of our data. But getting rid of all that noise already has a big impact. So using our Diff-in-Diff approach, we find that the savings from HVAC are about 2/3 of what was expected. And with our machine learning approach, they are about 80% of what was expected. Now, controlling for things matters, of course, but as you can see, the machine learning are quite stable and not necessarily sort of monotonically decreasing. In the Diff-in-Diff, they are a bit less stable, slightly smaller. This pattern also arises with light interventions. The estimates are 3/4 of what was expected actually delivered. A little bit of sensitivity with regards of what we control for. Again, we don't quite have one answer, but at least it's much more stable and it seems to be much larger. So overall, I think with the project, we want to achieve two things. One is to see how the machine learning is helping us pick up our controls and make sure we get an apples to apples comparison, but also think about measurement error in this context and see how can we help come up with the right number. As I said, compared to the literature, I would call it a 3/4 full glass. It's much more optimistic than previous estimates, but importantly, not if we look at the whole sample. So if we include all of these mismeasures and we include all of these outliers, we find very different answers. This means that we have work to do. We still don't have the answer, but we hope that with this, we will be able to think about how machine learning can help us in evaluating these energy efficiency programs more generally. Again, especially taking into account that measurement error might be a concern, and that also there is a wide heterogeneity across the treated units. Down the road, we just got the data yesterday, as I mentioned. We do have better cost measures, so we hope that we can also do a cost-benefit analysis. But for now, we just have to focus on the electricity data, which is the one that we actually can measure well. Yep. Any question or? Yeah. Thank you. Thank you. So I'm here at the Kellogg building, so yes.
Questions?
Change in the cost of electricity at different times of day? Does that have an impact economically?
So these are public schools. Our sense is that they are on a pretty flat schedule. I wouldn't expect them to be too responsive, but we can check. Our sense is that they are on a flat schedule. And these rates change very slowly. So even with a sample of 5 years, we would have limited evidence. There are some papers very interesting looking at households, typically randomized controlled trials that they force them into real-time pricing, and there actually you do see some responses. But here they are more or less on a flat. Yeah.
So you're predicting essentially what the is. Do you think about using the data to suggest where the greatest could come looking forward?
Yes. Yes. Yes, so one thing we haven't pushed is that we have this before and after, right? We come up with a prediction for a school, and we sort of come up with a difference between what should have happened and happened. So it's only 2,000 points in a sense, because we have 2,000 schools. But one thing going forward we can do is look at those savings and project them onto school characteristics. So for now, we didn't use many of the school characteristics because everything we have has an indicator for every school. And every single variable is school specific. But we do have information on their outer envelope. We have information on how many buildings they have. In California, many of these schools are a bunch of collection of little houses, basically. Whether it's good, I guess. So we have all that information, and what we think we can do is take the raw prediction error and project it into these school characteristics, see what we can find. Yes, but we haven't done it yet, so I cannot say. So I think we are definitely in conversation with them. We are getting the data from them, both through the Public Utility Commission and the utility itself. They are interested and excited about it, but a bit worried. As I mentioned, the economics people don't have a good reputation at giving big numbers. We have a very good reputation at giving really low numbers. And for the utilities and the Public Utility Commission, how well these policies look, it's mostly based on these ex ante energy savings. So if we found that they are 10% of what they expected, that would not necessarily be the best of the findings. But I think they are quite open. These are regulated utilities, and it's the Public Utility Commission. So they are slightly cautious about it, but excited. And we do present to them systematically to report. Yes. But I think they are cautiously excited, but a little bit worried. Yes. Yes. Yeah. No, so not for now. It's something we're working on. It's a bit less important than you might think. In our setting, what we care about is the average prediction. So the standard error on those predictions, given the data we have, is very, very small. We can account for it, but there is relatively little noise on the average prediction we come up with at the prediction step. That's not to say that the prediction errors, the prediction confidence interval is huge, but we care about average predictions, not the prediction distribution. So those are very, very small. We are working on making that correction, but it doesn't seem to be huge from what we can tell, at least for now. But the key is that we care about the average, not the prediction interval. The prediction interval is indeed huge. Mm-hmm. Synthetic, yes, yes. So we started the project without doing machine learning, and we started doing the project with matching. And part of why we went to the machine learning is that when you match, you exploit a lot other people, but you don't exploit your own. And in this setting, it felt like it was throwing away a lot of information. So we were having a bit of a hard time finding good matches, which wasn't intuitive to us because to us, schools are all the same. But then you look at the details, and a middle school will be very different from a high school. And in California, due to their climatic kind of particularities, some schools don't have heating at all. Some schools actually do heat. Some schools don't have air conditioning at all. So we found that it was much harder to find a good match than we think. And intuitively, it was especially true for the HVAC. The HVAC estimates were extremely sensitive to which matches we were accounting for. Synthetic control we haven't done. It's sort of similar in spirit, but not using your own. So we feel a combination of both would probably be the most efficient, but we haven't gone there. Yes, but the matching was sort of the motivation to do this, because even with matches, we were not getting rid of these kind of placebo trends. Yes.
You mentioned that there are different kinds of buildings. I mean, the heat exchange is going to be different in small buildings, surface area,
Yes.
to larger. So you use that as one of your variables, maybe the surface area that changes the heat with the outside environment.
So this, as I said, for now we haven't done, but remember everything we do controls for school-specific characteristics. I think going forward we can look at whether the treatment changes with those characteristics, but we haven't done it yet. Yes. So yeah. Yes. I see. So the adoption, I cannot remember. We have looked at adoption and whether there's selection in adoption, and as I said, they were bigger. They are also typically more south and more inland, which in California makes sense, especially for HVAC. I cannot remember if we included the age of the building, but we should. Yes, we should. And one of the challenges there is that I'm not sure we have it for every single school, but at least we should do it for the schools that we. Yes. Yes. Yes, and one nice thing about the data that just came in yesterday is that we had been asking for this for 2 years, I think, and now we got it. We know whether it's a replacement on burnout or whether it's a replacement of something that's relatively new or whether it's a replacement. So we will know whether they are replacing new stuff with even better or whether they are just installing something that they would install anyway. So we will know much more on that. Yes. Yeah, okay. Thank you.